start. Okay, last week we talked about hypothesis testing. So, in fact, what we did, I'm going to use this to illustrate the idea of hypothesis testing, and then it applies to hypothesis testing for different types of parameters. So, first of all, we have a statement, mu, okay, statement is concerned about the population mean equal to certain values. Mu does not equal to mu naught. So we choose between these two statements. So what we do is to collect a sample. But before that, for hypothesis testing, we set alpha. What is this alpha? This alpha is the chance of committing a type 1 error, all right, probability of committing a type 1 error. And what is type 1 error? Type 1 error, type 1 is the probability of you make a mistake when the null hypothesis is true. In this case, means that mu equal to mu naught. So when do we reject the null hypothesis? So we will design a rule. So what is the rules? So if you remember your hypothesis testing is something to do with this quantity. X bar tells you something about mu. So basically, I want to know whether this is true or not. I want to do not reject it. I compare the difference of these two. If the difference is huge, then I suspect the null hypothesis is false. But this difference depends, the magnitude of this difference depends also on the scale of your x. So if x is large, so of course x bar minus mu naught may be of a bigger magnitude. So we have to consider the variation of this x bar, which is supposed to be sigma over root n if we know sigma. If we don't know sigma, if you recall in chapter 6, we will consider this one. Why? Because we know how this what we call test statistics behaves. So this one follow normal distribution, standard normal. This one follow a t distribution with n minus 1 degrees of freedom. So now, whether this, based on sample, we calculate this test statistics value. If it is too extreme, how do I know whether it's extreme or not? So it's something like this. So this is our test statistics. Let me call it T. Let's look at this one. So this is the behavior of the test statistics, T. All right? So means 0, right? So 0. So we decide that, okay, if the T that you obtained from the sample is less than this number, that means fall in this region, or sets fall in this region, then we make a decision to reject the null hypothesis. So if the T that obtained from the sample falls somewhere here, then you do not reject. Your decision is you do not reject the statement because it's not too big. All right? Okay, so why we choose these 2 points? We choose these 2 points such that this probability is alpha over 2, this probability is alpha over 2. Which means that combining these 2 probabilities, it simply means that the chance of falling outside these 2 regions is alpha. So that is when the null hypothesis is true, we observe some extreme value. The chance is alpha. So that is the type 1 error. Okay? So we design the test statistic. So there are 2 scenarios. If this is known, then the T is x bar minus mu naught sigma over root n, and this follow normal 0, 1. So our decision rule is to reject H naught if the test statistics is less than Z alpha 2 or test statistics is bigger than Z alpha 2. All right? So we got the data, then we compute the X bar, and then compute the test statistics, and then check whether it falls here or here, then we reject. If it falls somewhere here, we do not reject. So this is called the critical value approach or critical region approach. All right. Alternatively, there's something called p-value. P-value, which is the probability of distribution or the random variable for the distribution of the test statistic follow, and this one greater than what you observe. All right, okay. For p-value, unfortunately for two sides, it's a little bit more complicated, is whether this observed value is extreme or not. This means that, what is T observed? T observed is to really compute from the data. This is still a random variable. Remember, I toss a coin. The outcome is head or tail. So this is a random variable. The outcome is either head or tail, or either 1 or 0. We don't know whether it's 1, whether it's 0. All right? So it's a random variable. But then when you toss it, it lands as a head on the top. Then the outcome is head. So we have the realization. So this is the realization of the sample mean minus mu naught sigma over root n. So this is what I called observed. So we compare this and this. All right. Take the minimum of the two. Take the minimum of the two, minimum, and then multiply by 2. That is the p-value. So basically, if I take a sample, if this is where my t-value is. So what is the p-value? The p-value will be this part and this part. Which one is the smaller? So this part is the smaller. I multiply by 2. So that is the chance, we call it the chance that you see something more extreme. I did not use the word bigger or smaller because it can be two-sided. So now it's here. So compare this one. This is the probability. Compare this side. This is the probability. So we take the minimum of the two and see whether it is very small. If this p-value is less than alpha, we reject the null hypothesis. All right? Alpha. This is alpha. All right. So the idea is that if the p-value is small, which means that the chance that you see something more extreme than what you see now is very small. So in other words, what you see in fact is quite extreme. So I always say that if you earn $1 million, but there are 99% of the people earn more than you do, you are not that rich. You are not that extreme. All right? But on the other hand, if I say you are very poor, or yes, you are poor because you earn only better than 1% of the population, then of course you are poor, right? Relatively, right? So that is how we define the extreme value. Can be bigger, can be smaller. Okay? So basically this is the ingredients of hypothesis testing. So from here onwards, we just talk about different hypotheses, different assumptions that will make our test statistics slightly follow a different distribution. It looks very complicated, very messy, but if you understand the idea, it's not too difficult. All right? Okay. In the last lecture, we somehow have not finished this one. Relationship between the two-side test, hypothesis testing, and confidence interval. So, the basic point is, if you construct a confidence interval for, let's say, mu, then if this confidence interval covers the value of the mu under the null hypothesis. This mu naught is the value mentioned in the null hypothesis. All right. If the interval covers mu naught, then it's equivalent to saying that we do not reject the null hypothesis. If your confidence interval does not cover this mu naught, all right. So that means if this is my confidence interval, all right, and it happens that the mu naught is here, then if you perform a hypothesis testing, you do all this work, you find out that you do not reject the null hypothesis. All right? But if the mu naught is somewhere here, all right, and this is your confidence interval based on the data, all right, it does not cover mu naught. So if you repeat what I mentioned about hypothesis testing, decide your test statistic, get the test statistic value, compare with the critical values, all this, then your decision, the final decision is that you reject the null hypothesis. So, in other words, the confidence interval and the hypothesis testing, two-side alternative, are equivalent in the sense that, here it is. This is the confidence interval. All right? The mu covered by this random interval with probability 1 minus alpha. If I rearrange it, there are two inequalities. Now, I have this x bar falls between these two numbers with the same probability. So, in other words, I will reject the null hypothesis if x bar, so now I replace this by the value of mu equal mu naught. Because under the null hypothesis, I'm saying that type 1 error is alpha, so this is not rejecting. X bar falls between, remember? I'm saying that these two values. So this is this value, and this one is this value. So the transform within this is 1 minus alpha, so outside it will be 1, that will be alpha. So this is saying that the test of the x bar falls within this region is 1 minus alpha. All right. So your decision is do not reject the null hypothesis. So the two are the same. All right. So if you don't get it, just remember, if you construct a confidence interval, if the confidence interval does not cover the value of the parameter under the null hypothesis, you can reject the null hypothesis. If it covers the value, then you do not reject the null hypothesis. All right. So here is the previous example. So we calculate mu equal to 34. The confidence interval based on this data, this set of data, is 34.08 and 34.92, which does not cover 35. Right? So if my null hypothesis is to test mu equal to 35, since the confidence interval, 95% confidence interval does not cover 35, so we reject the null hypothesis based on the confidence interval. All right? Okay, here's the p-value approach that I mentioned earlier. So the p-value sometimes is referring to the observed level of significance. What does, if you remember, level of significance, this part, is the probability of rejecting the null hypothesis. All right? So it is the probability of the test statistics greater than, let's say, the example that I used before, sigma is known, is something like this. It's 1 minus alpha. All right? Or rejecting the null hypothesis, if the null hypothesis is true. All right? So, sorry. This is alpha, not alpha, not 1 minus alpha. Okay, just remember, it's the probability of rejecting the null hypothesis, given the null hypothesis is true. This one, we fixed it at certain level. Then we construct our decision rule. So here, p-value is considered as, okay, because, okay, so in other words, you get a p-value. Let's say it is 0.15. So what does it mean? It means the probability of the test statistic greater than what you observed is 0.15, for example. All right. So, in other words, now I have this one, and I decide, I set my level of significance. Instead of 5%, now I set it as the same as the one that I have here. Okay, 0.15, maybe 0.16. So it looks not so clean. Okay, 0.16. So what does it mean? It means that based on the sample, I got this value. So now, based on this value, I make my decision. I get the null hypothesis. So then the question, because I make the decision, then I want to know what is the chance I commit a type 1 error. So the chance of committing type 1 error, you reject it wrongly, is 0.16. So that's why we call it observed level of significance. So let me repeat it. The level of significance is you fixed the level of significance. Then try to work out how to reject the null hypothesis. So the rule is that, okay, if your test statistic is greater than these two constants, in this case it's the Z alpha over 2 and minus Z alpha over 2, then you decide to reject the null hypothesis. So you fix alpha and then get the decision rule. So now I fixed the decision rule. So this is my observed value. Based on this observed value, I reject the null hypothesis. All right? So then you ask, so what is the chance of committing the type 1 error? So you calculate the chance of committing the error. So, in other words, the idea is like this. If you fix alpha, you have level of significance, fix these 2 points. So once it falls into this, we reject. So we fixed alpha, all right, given alpha. Then the chance of committing an error is alpha. And whenever your test statistic falls here or here, you reject. For observed level of significance, the story is like this. So this is the part. So this is what my test statistic value. So I work out the p-value. All right? So it is the smallest of these two times 2. So now I make a decision. Reject the null hypothesis. Look at what I have. I reject the null hypothesis. And you ask, what is the chance that you commit a type 1 error? So the chance is called the p-value, or the observed level of significance. All right? So in this case, so we calculate the p-value and compare with alpha. If p-value is less than alpha, then we reject the null hypothesis. If p-value is greater or equal to alpha, we do not reject the null hypothesis. Okay, I'm sorry, maybe I have to start with one side alternative. It's easier to understand. Let's do it again. We test this one against mu bigger than mu naught. Assume sigma is known. So my test statistic is x bar minus mu naught sigma over root n. And this both follow a standard normal distribution. If the alternative is true, you expect your x bar should be big as well. Am I right? Why? Because your mu is a number bigger than mu naught. So in other words, your x bar should be close to mu. And this mu is bigger than mu naught. Therefore, you expect your x bar should be bigger than mu naught. So if this is true, you expect a bigger, positive, bigger t value, the observed value. So in other words, my decision is to reject the null hypothesis if the test statistics falls greater than this Z alpha. Okay, maybe more specific. Alpha equal to 0.05, 5%. So I know this value, 1.645. All right? So whenever I compute my test statistics, okay, it is bigger than 1.645, I will make a decision, reject the null hypothesis, because that will indicate that X bar is quite far away from mu naught. So that's the idea. Now, suppose I got my test statistic value is equal to 2, then it's somewhere here. All right? So I reject the null hypothesis. Then what is the p-value? The p-value for this alternative hypothesis will be the chance more extreme than what you observed. In this case, what is more extreme? Huh? Bigger than what you observed. Am I right? Why is it bigger? Because my alternative is looking for whether mu is not mu naught, but mu is bigger than mu naught. So, for example, 1 million, again, go back to the 1 million, you earn 1 million. So if I'm interested in whether you are rich, that means I'm looking at bigger, on the larger side. So you're comparing how many people, or what's the percentage of people who have earned more than you do, right? Because you want to answer the question whether you're rich or not. So you look at the upper side, all right? You don't care how many people earn less than you do. So the same apply here, because you're taking mu greater than mu naught as my alternative. So I'm looking for, if that is true, mu bigger than mu naught, I expect the t should be bigger. So now I ask myself, what I observe from the sample, is it big? So to answer the question, I have to look for what's the chance that you will observe something bigger than what I have. If the chance is small, that means what I'm seeing is very extreme, very big. So that's the idea. So this p-value, all right, is roughly about 2.5%. Roughly, all right? If you observe about 2. Then this p-value is, for this value, the p-value is about 0.025. All right, 0.025. So it's small compared with 5%. So my decision is to reject the null hypothesis. Now, what happens if my observed value is 1.28, for example? 1.28. Then, according to the critical value approach, 1.2, okay, this is 1.645, this is 2, I'll observe. So now 1.28 is somewhere here. It falls in the do reject region. So my decision is I do not reject, because this value is not too extreme. It does not fall in the rejection region. And if I look at the p-value, then I ask myself, what is the chance that I will observe something more, bigger than what I have, 1.28? The chance is, if I'm not wrong, is about 10%. Okay? This area is about 10%. All right? So this 1.28 is not that extreme. It's only 10%. Why I say it's not extreme? Because we compare with 5%. All right? So 10% is not too small. That means if H0 is true, the chance that I see something more extreme or bigger than what I see now, which is 1.28, is quite high. It's 10% chance. So that number is not that small. Okay? So that's the idea behind p-value. So we have two approaches. One is to set up the region. Once you fall in this region, I reject. The other one is just calculate the p-value and then look at it, whether it's less than the alpha or 5%. All right, and then make the decision. Okay? Which one is better? P-value is more popular now because we can compute the probability. In the old days, we cannot so easily to compute the probability. So we set up a standard. All right? So this is why you have this normal table and all this. So you just set up the region and then. But the drawback of this critical value approach is that if I change my alpha percent, instead of 5%, you have to redo everything again. Not redo everything, but you have to recompute the critical region. While the p-value approach, I just based on what you observe, your sample, I calculate the p-value. For example, the p-value is 0.7, or sorry, 0.3, 0.03, 3%, what I mean, 3%. Then, for those who set alpha equal 1%, the level of significance 1%, then this 3% is not that small. Do not reject the null hypothesis. While if you set, beforehand you set alpha as 5%, then this 3% is too small. Then you will reject the null hypothesis. So you don't have to recompute the critical region again. Every time, you just look at your p-value, compare with your alpha, and then you make the decision. All right? So now with n equal 49, sigma equal 1.5. So now the sample mean, x bar is 34.5, and we want to test h naught mu equal to 35. All right? So how likely we will see this? All right? Now, because we did not specify whether we are interested in the alternative mu bigger than 35 or less than 35, we did not specify that. Therefore, we include both. That means mu can be bigger than 35, mu can be less than 35. So to combine them is equivalent to mu does not equal to 35. So that is our alternative. So the p-value, all right, okay, so this one, we translate 34.5 minus 35 divided by 1.5 divided by square root 49. So that is my test statistic. So here I use Z, but it basically is just a test statistic, which is x bar minus mu naught over sigma over root n. So the value here is minus 2.33. Minus 2.33. So ask whether this is extreme or not. Because it's a two-side alternative, so you have to look at what's the chance smaller than minus 2.33. The chance is the chance is 1%, 0.99%, about 1%. While if you look at whether this is too big or not, then the chance of bigger than minus 2.33 is about 99%. All right. So in order to compute the p-value, we take the minimum 2, the minimum 2, and then multiply by 2. All right. So the p-value turned out to be this. Okay. So the p-value is 2 times 0.0099. So it's about 2%. About 2%. So that's the p-value for the two-side alternative. For the two-side alternative. So it's so small, less than 5%. So we reject the null hypothesis. And in fact, it's the same conclusion if you use the critical value approach. So here is the critical value approach. You will reject the null hypothesis. Is false here or false here? It happens that minus 2.33 falls in the rejection region. So the two approaches, whether you use critical value approach or use the p-value approach, the conclusions are the same. All right? So we compare, and this is less than 5%, so we reject the null hypothesis. All right? Okay, how about one-side alternative? After string is almost the same. The test statistics is the same as before. Only the decision rule you have to modify a bit. All right? So the decision rule is whenever the Z observed is bigger than Z alpha. Z alpha, okay, you can think of it like this. This is the Z alpha. For one side alternative mu bigger than mu naught, we look for bigger Z value. Am I right? Because x bar is a value bigger than mu naught. So you expect this to be close to mu, which is bigger than mu naught. Therefore, this one is big, a positive big number, if the alternative is true. So we look for, so we reject if our observed value is false here. So this is the rejection region. Get the data, compute the set observed. Means you compute x bar minus mu naught over sigma over root n. All right. So this is the picture. All right. This is the alpha. So you check if your observed value falls here, you will reject the null hypothesis. All right. So this side you do not reject. Okay. How about alternative mu less than mu naught? The same statistics, but now we'll reject whenever the observed value is less than z minus z alpha. All right? So it's like this. So this is the z. Oh, this is the z minus z alpha. So this is the region for which you reject. So you calculate, get a sample, calculate the data. Oh, save some energy. So you calculate your, yeah, that's why I feel more comfortable now. Save the world, save the earth. All right. Okay, so we'll reject if your test statistics value falls in this region. All right. So here's an example. All right. So here is a claim. The manufacturer developed something new synthetic fishing line. You develop something, then it has to be better, right? Better. You cannot say that, okay, my new fishing line has a strength. It's different from the existing one. Yeah, different. I don't want to be worse than the existing one, right? So it has to be better. So better in the sense that the strength of your fishing line is better than the existing one. So this is the claim. Where mu, what's mu? What's mu? Mu is mu law. In this example, mu means the average strength of the fishing line for this manufacturer. This is the mean strength of what? Of the new fishing line. All right? Because the manufacturer claimed that this average, the mean, is better. It's better. So that means it's stronger than the existing one. And this is the existing value. All right? So we want to establish this fact. Right? And the old belief or the status quo is that your new fishing line is the same as the existing one, the market one. So this is the null hypothesis that we want to reject, right, and favor to the alternative, which is greater than 8, right? So sometimes it's confusing. So always remember, we look for evidence to build up something new. So in other words, we try to protect the status quo, the old belief. So what's the old belief? Thing is the same as before. So whatever your new fishing line is, it's the same as the old one. That's what we believed. All right. But now this manufacturer is saying that it's better. So you have to test mu bigger than 8. Right? So I look for a sample and do experiment to find out the strength and then do some tests. Now, if you believe mu is bigger than 8, the manufacturer claims mu is bigger than 8 and you believe mu is bigger than 8, what's the point to do all this hypothesis testing? You agree, I agree. Okay, so mu is bigger than 8 now, right? So that's why you have to look for evidence, all right, to show that mu is in fact different from egg. And what is this egg? This egg is the existing strength for the existing fishing line, or the markets, the fishing line that you can find in the market. So the standard deviation is known. Look at it, it does not say that this number is from sample. It's from the knowledge. We know sigma. So everything is there. So now we got it. N is 50 and X bar is 8.2. Hey, you don't need to do any testing. 8.2, even primary school students know that this is bigger than 8. Huh? Right? Yeah, that's for primary school students. What we are saying is that mu equal to 8. The population means 8. All right? Unless you check all the fishing lines and then get the average. See whether it's equal to 8. If you are able to check all, which I doubt, right? From the past, to the future, so many fishing lines produced. All right? So you cannot test all. So you don't know mu. So what we have is just a sample of the fishing lines and test the strength and get the average 8.2. All right? So you may get another sample, which may be you have a mean equal to 7.95. All right? So this is a random variable. It depends on your sample. So you cannot just base on the sample and then conclude that mu equal to 8. I mean, you have to do some statistic hypothesis testing. All right? So this is how we do it. So we test the manufacturer's claim. That means we want to see whether we can reject the null hypothesis and favor the alternative, which is the manufacturer's claim. All right? Alpha set at 1%. So we proceed. First of all, we, by the way, please, when you try to answer the question, you cannot just say, oh, my hypothesis test mu equal to 8. Hey, sorry, sir, what is your mu? So you have to say what is mu. Mu in this case is the average strength of the fishing line or the new fishing line by this manufacturer. All right? And the hypothesis, again, we have to write down the hypothesis. The null hypothesis as well as the alternative hypothesis. Why do we need to write down the alternative hypothesis? Because the decision rule is based on your alternative hypothesis. Although everything is computed under the null hypothesis, the p-value, the probability of committing type 1 error, all these things are assuming the null hypothesis. But which side or both sides that you have to consider, you need to know the alternative hypothesis. So in this case, we are testing mu bigger than 8. So set alpha equal to 0.01. All right. We have not touched on, look at the data. So all set, then we decide on the test statistics. The test statistic is X bar minus 8. This is mu naught, which is from the null hypothesis. All right? And this is sigma, and this is n. So it's sigma over root n. This is test statistics. And this follows a normal distribution. If the underlying distribution is normal. Is the underlying distribution normal? So I go back to check the question. Is this given? I searched. I couldn't find the word normal. Then I asked, what is the distribution of this? What is the distribution? X bar minus mu over sigma over root n. Is this still standard normal? You don't know. This magic theorem, big sample. Yeah, the magic theorem is the central limit theorem, which requires what? Requires the sample size to be big. Do we require normal distribution for the population? No. All right? Central limit theorem, basically, you don't need normal distribution. But our version requires the variance to be finite. Otherwise, how can you divide by sigma over root n where you got sigma? If sigma is not finite. All right? So we apply the central limit theorem. It is not exactly standard normal, but approximately normal. All right? Okay. So from there, I know how this behaves, so I can get this value, 2.326. 2.326. 2 minus 2.3 is one side. So this is 1%. The chance of force greater than 2.326, the chance is only 1%. So if my observed value, that means I take the sample, substitute x bar and get the value is bigger than 2.326, I decide to reject the null hypothesis. So that means, yes, the manufacturer is really right. The strength, the average strength is bigger than mu, bigger than 8. All right? So we compute this. A little bit confused. Sometimes it's capital letter, sometimes it's lowercase. So just always remember, big capital letter represent random variables, which you don't know the value. You only know how it behaves. Random variables. That means it can be any values over the range and take certain probability or probability density. Lowercase are constants. And these lowercase are taken, this x bar, the lowercase x bar, represent the realization of your sample. That means once you take a sample, you check it, you observe x1, x2, up to xn. So you got all those values. All right? So that is algebra. All right? I did not write down what is x1, but it means that you know what x1 is. They are known. And then you calculate the average. So you can calculate your lowercase z. Compare with 2. Okay, so I calculate it's 2.828. So the p-value is approximately about 2%. This one you can look it from the normal table, or you can use your software to get it. Okay, I don't have time to go we have already discussed in chapter 6 how to get this probability. All right, so now finally we make a decision because the observed value falls in the critical region. That's one approach. All right, that is 2.326. And now what I observe is 2.828. This is the rejection region, so I reject it. And at the same time, the p-value is here, which is less than 1%. Am I right? Okay. Yeah. Now, just in case you don't have your graphic calculator, you don't know how to use it, you don't have a computer with you, you don't have the tape, or you just have the table with you. All right? So at least I know one point. 2.326. Bigger than this number. All right? It's only 1% chance. 1% chance. All right? So now my number is greater than this 2.326. Although I don't know the p-value. But I know the p-value must be less than 1%. Am I right? Let me repeat. I know this is the point. Bigger than it, that means this part is 1%. This area is 1%, right? And your value, 2.828, is on the right-hand side. So what can you say about this probability? Relative to 1%. Much smaller, right? So I don't know the p-value, but I know that it's less than 1%. I want you to know, if I don't have this computer, what can I do? At least I can make a decision. If I know this 2.326, okay, greater than it is 1% chance. All right, so the decision is to reject the null hypothesis at the 1% level of significance. Usually, when you reject the null hypothesis, you better stay. I make this decision, and I tell you what is the type 1 error that I take the chance. I take the chance of 1%. There 1% chance that I make a mistake for this decision that I have. All right, 1%. That's the level of significance that I do. Okay, so this is the picture to illustrate. So z equal to 2.828. All right, it's just one that I just showed you. So we reject because it falls in the critical region. P-value approach, this is the point. I calculate the p-value, which is bigger than it. So the chance bigger than it is 0.00233. All right, so, and this is less than 1%, so we reject it. All right. Okay, so we reject the null hypothesis. Okay, how about the variance unknown? Now, so still the same type of hypothesis. Like for example, you want to test mu equal to mu naught against mu bigger than mu naught, for example. Can I still use this one as my test statistics? Cannot, huh? Why cannot? I don't know sigma. I don't confuse. I don't know sigma. And I still can guess what is it. Just like in the exam, you don't know the answer, you still can guess the answer, right? Run something, try something, right? So that's your guess. All right, so the same here. You don't know sigma. You cannot use this formula because you don't know sigma. But I can guess or estimate sigma. So what's the natural choice? Sample standard deviation, S over root n, right? Then the next question is, how does this behave? What distribution does it follow? So this follow a t distribution with n minus 1 degrees of freedom. All right? So then I will reject, let's call this, if the observed statistics value is a number that got from this distribution with alpha. All right? That means this is a t distribution with n minus 1 degrees of freedom. This is a point, such that bigger than this point, that the value, the probability is alpha. That is what this point means. T n minus 1 semicolon alpha. All right. So, just repeat what I just discussed in the previous case when sigma known. Whenever this one is bigger than this, I reject the null hypothesis. If the observed value is less than this number, I do not reject this and favor this one. All right? I will not reject it and favor this. So, what happens if I'm looking at mu at this alternative? Then same thing. You check your observed value. So if this is true, what do you expect about the t? Is it big or small if the alternative is true? Your mu is less than mu naught. So that means your x bar should be less than mu naught. Why? Because x bar is supposed to fluctuate around mu. So if mu naught is there, your mu is here, your x bar is somewhere here. Of course, your x bar will be less than your mu naught. So we will expect a small value for the test statistic. All right? Small means negative, very big negative number. All right? So we'll expect this less than minus t n minus 1 alpha. Okay? This is the number, minus t n minus 1 alpha. All right? So that this probability is alpha. Because t distribution is symmetric about 0. About 0. All right? So bigger than t alpha, t n minus 1 alpha, when you flip it to the other side, it becomes negative. And less than that number will be alpha. All right? So, now here I forgot to mention one thing. In order this is true, remember I mentioned 3 conditions. Underlying distribution, whether it's normal or not. Second one is whether we know some of the parameters. Like in the previous case, we know sigma. Now in this case, we don't know sigma, so we use S. All right? So now, in order this to be true, you need the underlying distribution should be normal. All right? Okay. So now, how about the alternative? Mu does not equal to mu naught. Now this alternative is equivalent to the previous 2. Either one of them. Is mu may be less than mu naught, or mu may be bigger than mu naught. So that's why we say that it does not equal to mu naught. So the rule will be like this. It can be too big, but we have to do a minor modification. We make it alpha over 2. And, or, the observed value is too small. Smaller than this number. Why I change to alpha over 2? To make sure that the probability now, add up the 2 sides, give you alpha. So each side is only half of alpha. All right? Okay. So here it is. When variance unknown and the underlying distribution is normal, so this is what we do. Test statistics. Remember, we're talking about underlying distribution normal. So this is what we have. All right, for 2-side alternative. One side bigger than I minus 1 alpha. This side less than minus Tn minus 1 alpha. All right, so here is the example. The average length of the students registered for summer courses at a certain college has been 50 minutes. So now we have start a new registration procedure and see whether it improves or not. Just like you try your new Luminous last semester, right? Okay, so a random sample. Oh, you didn't have experience of using this Luminous last semester. Right? Before that we use, what did we use? IVLE, right? So we get so used, not you, but I used IVLE for so many years, right? Suddenly it changed to Luminous, so there's some teething problems. All right, anyway, so this is a new registration procedure. So we apply and for 12 students, and it takes 42 minutes to finish it. All right? Now, so don't jump to the conclusion because it's 42 is less than 50, so this is better. Maybe you take another 42 students, the registration average time is maybe 60 minutes, right? Because this is a random variable. So you have to identify this is the O1. So now we are talking about mu. Mu is the average time for registration for this new procedure. All right? For this, mu is for the new procedures. The average time for registration for this new procedure. So this 50, all right, is the the existing one or the old one. So I want to establish that mu, I want it to be better. This time better is not longer, it's smaller. So I want to establish that mu for the new procedure is less than 50. Am I right? You don't want to test mu that's not equal to 50, right? What's the point to have a new procedure which can have an average time longer than the old one? All right? So you want to test mu equal to 50. This is the existing, the status quo. And you want to look for evidence to reject this status quo, get a new statement. This is x bar, this is n, and what is this? Standard deviation. This is from the sample. So this is the sample standard deviation. So this is S, the sample standard deviation. All right? So told that the alpha is 0.05, and in fact, I'm sorry, okay, I did not think carefully. I mentioned it, but what I wrote down is wrong. All right, I said that it should be less. Right, better means you have the shorter time for registration. So mu should be less than 50. All right. I still can correct it in the exam. Once you submit it, you cannot correct it. So make sure that you understand. You want it to be better. All right. Now, but if there's reason or there's no reason, no implication, no tips, nothing to tell you whether it's less than or greater than, then you take the safest equal. So your alternative will be not equal. All right? Just simply say that. All right? Okay. So this is the assumed normal. If it's not normal, then what can we do? If we don't have this assumption, can we apply the central limit theorem? Yes and no. Yes. Okay, no, because the sample size is so small. But then you're just sitting there do nothing, right? So we still try. But remember, the approximation may be very, very bad. All right? That means your answer may be slightly better than no answer. All right? Because we don't know the underlying distribution. But I would say that if the underlying distribution may not be normal, but if it's symmetrical or close to normal, then you can still use the central limit theorem. All right? So it's not cast on so black and white. 30, less than 30 cannot use. There are some other things that you have to consider. All right? Okay, we don't have this worry because we are told that it follows normal distribution. All right, so we set up the mu. I'm sorry, I forgot to mention mean registration time for the new process, new procedures. All right, this mean we are referring to the new procedures, the mean of the new procedures. All right, so this is what we try to test: set up alpha, and then set up the test statistics. And what is the distribution of this test statistics? Because it's normal, so we know that this follows a t-distribution with n minus 1. Why I need to know that? Because I know that, then I can set up my critical value. I can set up my critical value. And also, if you may need to compute your p-value. All right? So it's 1.796. So you get your data, compute your observed value. If it is less than minus 1.798, then we reject. Why the suddenly negative value? Because 1.796 is this value, bigger than this value. This is what it means by this our notation. Bigger than this number with a probability 5%. So this is 5%. But we are looking for a value for which smaller than that value is 5%. All right? So I want this to be 5%. So what is this value? Because it's symmetric about 0. So it's just like a mirror putting at the 0. It reflects it. So this is minus 1.796. And this area is the same as this area. So we are comparing with minus 1.796. All right? Okay, so now I compute the test statistics. It's minus 2.329, which, all right, this number, all right, see? Okay. So here is the p-value. We don't have that in our t-table. We only have these two numbers. Okay. One is 2.329. Bigger than it, 1%. The other number is 2.201. Bigger than it, that means this whole thing is 5%. 2.5%. 2.5%. All right? So my 2.326 is somewhere here. Okay? Oh, okay, I read it wrongly. So this is 2.718. So 2.329 is somewhere between these two numbers. Although I don't know the p-value, but I know that it has to be between 1% and 2.5%. Am I right? So the area is bigger than 1%, but less than 2.5%. So the p-value is between 1% and 2.5%. So I can make the decision. Because that is between 1 and 2.5%, it must be less than 5%. So I reject it. I don't really care to get the exact p-value. All right, so we reject the null hypothesis. Based on the critical value, because this number is smaller than this number, so we reject. It's less than the critical value. So it's fall in the rejection region, so we reject it. Or the p-value is somewhere between 1% and 2.5%. In fact, it is about 2%. So we reject the null hypothesis. Okay? Let me make it clear. We want you to make the decision. If you want to make the decision based on the p-value, and if you cannot get the exact p-values, you just make your decision based on some idea about the p-value. So in this case, I have not computed using, if I use the statistics table, I only know that it's somewhere between this number and this number, which I know the probability greater than these two numbers. Greater than 2.7 is 1%. Greater than 2.2 is 2.5%. And this value that I observe is somewhere between these two numbers. So the p-value must be between 1% and 2.5%. So I can make the decision. So let me ask you, if at the beginning I don't set 5%, but instead I set 1%, so what's your conclusion? Based on, I don't know the exact p-value, but based on the argument I just have, do you reject the null hypothesis? If my alpha is 1%. What's the p-value again? We don't know. But we know it's between 1% and 2.5%. That means it's bigger than 1%, but less than 2.5%. So, if you use 1% as a reference, what the p-value that I have, although I don't know the exact value, but it's bigger than 1%. So my conclusion is that I do not reject the null hypothesis. All right? So it's not too difficult to see if you understand the process. All right? Okay. How about differences? Okay. So first of all, start with variance the same. So we want to test. All right? mu1 equal mu2 against mu1 minus mu2. To make life easy, just consider one side bigger than 0. So what is the test statistics? If these are known, then we look at this. You look at it. We are looking at x1 bar minus x2 bar. Why we look at this x1 bar minus x2 bar? Because this is how we have some idea what mu1 minus mu2 should be, right? Based on the data, based on the sample, the two samples, then we got the idea of mu1 minus mu2. Then the expectation of this is equal to mu1 minus mu2. So it's just a random variable minus its expectation. And then divide by the variance of x1 bar minus x2 bar. This is the square root of the variance of x1 bar minus x2 bar. So this whole thing is normal distributed. All right? Then the rest is just like what we discussed. All right? You have the test statistics, get the sample. So this time you have two samples, calculate x1 bar, x2 bar, substitute. Under the null hypothesis, what is mu1 minus mu2? 0, under the null hypothesis. All right? And sigma 1 square is known, sigma 2 is known, so we can compute it. And then what we compare is compared with Z alpha. All right? But the same formula can also be used even if the underlying distribution is not normal. We don't know the underlying distribution. But provided that these two sample sizes are sufficiently large. When we say sufficiently large, maybe bigger than 30. All right? Then we can still use this result or this procedure. But just bear in mind, in that case, this is only approximately normal, a standard normal. But the way that we do things is the same. All right? Okay, so here is an example. I have N120, X1 bar 29.8, N2 25, X2 bar 38.7. Wow, they're very different. All right. But we are told that sigma 1 is 4, sigma 2 is 5. And now we want to test whether mu1, mu2 are different. That means I want to know whether mu1 minus mu2 equals 0. What is the alternative? So I set mu1 minus mu2 bigger than 0 or mu1 minus mu2 less than 0. We don't have any preference. So not equal. So the alternative is not equal. All right? Unlike in the previous example, whether the new procedure is better, so we test mu less than 8. This time we don't have any favor whether this method is better than the other, because it did not mention in the question. All right? And we assume that it's normal. All right? So we just proceed. Okay. So these are the mu's, the hypothesis. So remember, mention what is mu1, mu2. What are mu1, mu2? Set up your hypothesis and the alternative, and also set up your alpha. Don't set up the alpha, the level of significance, after you calculate your test statistic value. All right. Okay. So this is our test statistics. It follows standard normal distribution. So at 1%, so now I want, so that, because it's two sides, so therefore this has only 0.5%. And the other one have another 0.5%. Because it's a two-side alternative, that's why we have to prepare for the test statistic can be very big, so it falls over this region. And also it can be very small, so it falls another region. So I make sure that I cover both sides. So, but the total, the probability of committing type 1 error is only 1%. We set at 1%, a very high standard. Very difficult to reject the null hypothesis. We set committing error with only type 1 error with only 1%. So I divide into half, so each side has only 0.5%. So we reject if Z is less than minus 2.57 or Z greater than 2.57. So this is the Z. And from the data, we got minus 3.65. Wow. Is it very small? Yes. Why? Because we compare. Okay, I did not write down the p-value. Sorry, the critical value. What is that? 2 what? Yeah, 2.5758. So this number that we obtained here this number is less than minus 2.728, right? So, we reject the null hypothesis. At the same time, we look at the p-value. So this is what we observed. So we compute this probability as well as this probability. And then take the minimum, multiply by 2. And this is the answer. It's very small. All right? So we reject the null hypothesis. All right. So how about if the variance is not known, but the sample size is big? All right? Then, because it's a large sample, so we think of it, we still look at this one, minus mu1 minus mu naught. So instead of sigma 1 square, which we don't know, right? Unknown variance. So we replace by S1 square. And sigma 2 square, we don't know, replace it by S2 square. What is the distribution of this one? We don't know. But we know that this is approximately normal. All right? Why? Because if the sample size is big, we can say that S1 square is very close to sigma 1 square. So we replace it by sigma 1 square. But because this is only a guess, so it's not exactly a standard normal distribution, but approximate normal distribution. All right? And so that's what we have. So okay, where's my, okay. So I just repeat everything except that now I don't know sigma 1, but I use S1 and S2. All right? This is the X1 bar and X2 bar, N1 and N2. All right? But what is the hypothesis? So it's important to choose a lower value of thermal conductivities. This is what we want to find. We have two types, and we want to know whether one has a smaller or lower value of thermal conductivity. When we say a low value of thermal conductivity, we are looking at the average thermal conductivity of those types. Just like whether male is taller than female. I can always pick one short male and one tall female and conclude that male is shorter than female. But this is not what we accept. When we say male is shorter than female, we're talking about the average height of the male is shorter than the average height of females for the population. All right? So the same apply here when you say it. So we're talking about all the the construction, roadway construction using this for concrete, or two types, great aggregate and no fine aggregate. All right? So, now here is the hypothesis. This is the question that you are asked. Whether the great concrete exceeds the no fines concrete in terms of the average thermal conductivity. All right? Now, so, which one is 1, which one? Okay, I can take this as 1 and this as 2. It doesn't matter which is 1, which is 2. So, you have to set your alternative correctly, reflect what you are asked to do. So here, my alternative will be mu1 exceed mu2. That means I'm doing this. If I choose this as mu2. But if you take grade as mu2, and then no find as mu1. Then you have to adjust your alternative accordingly. It doesn't matter. But you have to do it consistent. So if I define 1 for the great and 2 for the no finds, then mu1 minus mu2. So when I say the true conductivity of this one exceeds the true conductivity of no finds concrete, then it means mu1 minus mu2 bigger than 0. All right? Okay. So I just proceed. And this is my test statistics. I just replace, I don't use sigma 1 and sigma 2 because I don't know them. Now I use the sample variance. So this one follow approximately normal. So that's why lead to this critical value. All right. Because we're talking about mu1 minus mu2 bigger than 0. So we expect bigger value for this if the alternative is true. That's why this bigger than this number is our rejection region. All right? So the rejection region is whenever Z is greater than 2.3263. So from the data, we got 3.335, which is bigger than 2.3. So we reject the null hypothesis. All right? And at the same time, you can calculate. If you have a computer or graphic calculator or whatever, you can calculate it. If no, you look at the normal table, you get approximate value. You get approximate probability of Z greater than 3.35, 3.33. All right. All right, so this is our conclusion. We reject the null hypothesis. Oh, by the way, we reject the null hypothesis at this level of significance. But please, some people may not understand all this. They want to have a conclusion in plain English. What's the question? The question is whether the true conductivity of this great concrete exceeds the average conductivity of the no finds concrete. So the data suggests that the average thermal conductivity for this great concrete exceeds the other type, the conductivity of the other type. All right. So write down the conclusion in words, if you can. Okay. Now, if variance known, we know how to deal with it. If variance is not known, but sample size is big, we can do it. All right. But how about if we don't know what they are, but we know something about it? We know that they're equal. We don't know them, but we know that they're equal. All right. When I say unknown, I don't know what is sigma 1 and what is sigma 2. But although I don't know the value, but if you know that they are equal, because a lot of the problems, the variance of the two populations may be the same. So we make use of this because, as I mentioned in chapter 6, so we use this to estimate sigma 1 square. We use this to estimate sigma 2 square. So if they're not related, they are not equal, then it's okay. But now once we know that they're equal, then the question is, are you estimate? So can I still proceed to use S1 squared to estimate this? But then now I have two estimates. We're supposed to estimate the same thing. So can I have a better estimate? So the answer is yes, you can have it. One simple way is take the average of the two, right? But this is not ideal. Why? Because the estimate, how good an estimate is, also depends on the sample size. If the sample is big, you have a better estimate. So therefore, we would like to take the weighted average. So that's what we talk about in chapter 6. So if I call this sigma, then sigma square is estimated by something we call pooled variance. So it is n1 minus 1 times s1 square plus n2 minus 1 s2 square divided by n1 plus n2 minus 2. So it's the weighted average, all right, weighted by the sample size minus 1. Big sample, minus 1 is still big. So you put more weight to that estimate. Okay. But this needs the assumption underlying distribution is normal. And small sample size. I want to know, if the sample size is bigger, can I still apply what we're going to derive? Okay. Maybe let's see what we do. All right, so referring to this section 6.4.3. So, okay, this is an example. But basically the idea is like this. Minus x2 bar minus mu1 minus mu2 divided by the sigma are common. So this is the variance. This is not the one. This is not the answer. Not yet. This is just the intermediate step. Take the square root. We don't know sigma square. So we replace it by the estimate. This usually we use the notation. The notation that we use is SP, the pooled variance. Pool the two samples together. All right? This one will follow a T distribution with n1 plus n2 minus 2 degrees of freedom. And all this does not depend on the sample size. So for small sample, you can use it. For big sample, you can also use this formula. And what do we need? We need two things. First of all, the underlying distribution is normal. Even this one, we can modify it. Okay, but let's assume the underlying is normal, and we don't know the sigma 1 and sigma 2. But we know that they are equal. So I can use this formula. So it does not require the sample size to be big. All right? Now, what happens if the underlying distribution is not normal? We don't know whether it's normal or not. We don't know the variance, sigma 1, sigma 2. But we know that they're equal. All right? That's it. One more thing. We have big samples. N1 and N2 are big. So we don't have normal distribution. All right? We don't know the variance, but they are equal. We know that they are equal. And we have big sample size. So will this still true? Okay, yes and no. It's not true, but you will replace it. But this time, this one will follow what? Approximately standard normal. Your sample is big, otherwise it's not true. So maybe the idea is that whenever you don't have the normal populations, all right, then you need big samples, all right, bigger than 30, all right, in order to apply the central limit theorem. And in fact, one more, the weak law of large number, but just apply the central limit. And then we've got an approximate distribution, approximate normal distribution. So that's the idea, all right? No normal population, you compensate with large samples. And then if sample size is not big, then what? Sorry. Nothing, or you still use the normal approximation. but remember the approximation may be very bad. Okay, so here is example. So we have N1 equal 12, N2 equal 10. They go through different courses. One is the boring conventional classroom procedure. The other one is programmed materials, maybe sit for the watch your webcast. All right. So at the end of the semester, both of these two groups set for exam, same exam. So this is X1 bar, S1. All right. And this is X2 bar and S2. All right. This is X2 bar. Test the two methods of the learning are equal. So what does it mean? It means that what we really want is to find out whether there are difference or not. But we did not show which direction to go. So basically the alternative is mu1 does not equal to mu2. Okay? So here we assume that the approximation, the distribution is normal. Maintain normal. All right? Don't confuse. Here we are saying that the underlying distribution is close to a normal distribution. So that's why we use normal approximation. Here we don't never mention about central limit theorem. So we don't require a big sample size. We're just assuming that the underlying distribution is normal. But just play safe. So we say approximately normal. You can consider it's very close to normal. So with all the property of known underlying distribution applied here, and also assume equal variances. All right. So then, so we proceed mu1, mu2, and we test mu1 minus mu2 equals 0 against mu1 minus mu2 not equal to 0. Set alpha as 0.1, that means 10%. So we use the T, this one, or the test statistics. All right, is something like this. X1 minus X2 bar minus the mu1 minus mu2, SP, take it out. So this follow a T distribution with N1 minus plus N2 minus 2. So that's how you arrive at these critical values. Oh. I think there's a typo here because it's a two-side. So this should be alpha over 2. But alpha is 10%. So alpha over 2 is 5%. So that's why this is 0.05. All right? So there should be over 2 here. All right? Because we are looking on two-side alternative. All right? So this is the pooled variance. And we, based on the data, we calculate the pooled variance is 20.05. And finally, we got our test statistic, 2.08. Another typo here. So this should be 2.086. All right. So, it turns out it's 5%. The p-value is 5%. So, because the chance of bigger than this number is 0.025, less than it is 0.975. So 2 times 0.025, 0.05. So 1%, sorry, 10%. So this number is more than 10%, more than 0.1. So we reject the null hypothesis. Or this falls in the rejection regions. So we reject the null hypothesis. All right, so here's the conclusion. All right, so we reject the null hypothesis and saying that based on the test result or the exam result, these two methods, all right, are different. But I did not say which one is better. Okay, so I think I have to stop here. We're sorry that the tutorial questions cover the whole chapter, and we have just finished this part. All right. So I believe that you can try it out yourself. And Thursday, we still have lecture. We have all finished this chapter 7, right? And we are going to do a revision on this in the last lecture on Thursday.